Hello everyone, I'm Sunita from SNS College of Technology, Department of Mathematics. So as the continuation of the lecture series in eigenvalue problems, here we are going to see a topic called applications of Cayley-Hamilton Theorem in this lecture video. First is introduction to Cayley-Hamilton Theorem. So here the Cayley-Hamilton Theorem statement is every square matrix satisfies its own characteristic equation for an n by n matrix A if P of lambda is equal to determinant of A minus lambda I is the characteristic polynomial, then P of A is equal to 0. Significance: a foundational tool in matrix analysis with wide applications. P of lambda equal to lambda square minus trace of A into lambda plus determinant of A. Next, application 1. So here the key point is simplifies computation of higher matrix powers A power k where k is greater than or equal to n using lower powers. Next, we are going to see the explanation of this. Since P of A is equal to 0, higher powers are expressed as A power n minus 1 etc. up to A and 1. Here A square can be given by trace of A into A minus determinant of A into I. Next, second application, we can find the matrix inversions. So enables finding the inverse of a matrix using its characteristic polynomial. So the formula is for a 2 by 2 matrix, A inverse can be found using 1 by determinant of A, trace of A into I minus A. So when A matrix is equal to A, B, C and D, then trace of A inverse can be found using 1 by AD minus BC into D minus B minus C and A. Next, third application is solving system of linear equations. So here, which helps solving Ax equal to B by computing A inverse via the theorem. So the explanation is we are having two equations, 2x plus 3y equal to 5 and 4x plus 5y equal to 6. So here this x can be found using x inverse equal to A inverse B. Next is stability analysis. So here the key point is used in control theory to analyze system stability via eigenvalues. So here this tries the characteristic polynomial to system behavior. Next is diagonalization. So the key point is connects to diagonalization if A is equal to P dP inverse, then P of A equal to 0 holds. So for the example, reinforces eigenvalue and eigenvector properties. D equal to lambda 1 0 0 lambda 2. For example, if we are having a 3 by 3 matrix, the diagonalization process will get the final answer D as lambda 1 0 0 0 lambda 2 0 0 0 and lambda 3. Next is we are going to see an example problem. So here the problem statement is find the inverse of A equal to 1, 2, 3, 4 using the Cayley-Hamilton theorem. So here the first step is to frame characteristic equation. So P of lambda equal to determinant of A minus lambda I. So to find A minus lambda I, we can apply minus lambda in the diagonal element. So we will have A minus lambda I equal to 1 minus lambda, 2, 3 and 4 minus lambda. So on taking the determinant for that matrix, we will get 1 minus lambda, 4 minus lambda minus 6. So on simplifying that, we will get lambda square minus 5 lambda minus 2 as our equation. Now using the Cayley-Hamilton theorem, we are going to transform this lambda into A. So we will have A square minus 5A minus 2I equal to 0. Next, we have to solve. So for solving A inverse, we have 1 by AB minus DC, that formula. So we'll have 1 minus 1 by 2 into A minus 5I. So on computing, we will get the A inverse to be equal to 2 minus 1 minus 1.5 and 0.5 as our A inverse. Here these are the reference for the Cayley-Hamilton applications. Next, summary. So this simplifies matrix operations across multiple applications. Next is key takeaways. So essential for matrix power. Next is inversion, system solutions, stability and diagonalization. So this Cayley-Hamilton theorem is used in various fields. Thank you.